In this video, let's model two-person games that have no saddle points with linear programming to find the optimal randomized strategies. And then we are going to solve the linear programming models using some concepts from the duality. So let's start. Given the reward matrix for this game in this example, you see that this game has no saddle point. It means that the optimal strategies is not pure strategies, but randomized strategies. And also you see that we have no dominated strategies. So we do not have rows or columns that we can eliminate. Okay. So to formulate the linear programming model for the row player, let's start by, as usual, thinking that as row player, the player cannot control whatever strategy that is played by the column player. Therefore, we have the constraint if the column plays the first strategy for column, if the column plays the second strategy, and if the column plays the third strategy. And these are the expected reward for the row player with respect to the row strategy of playing x1, probability of playing the first row strategy, and x2, the probability of playing the second row strategy. And then after listing all this expected reward with respect to each strategy of the column player will pick the minimum among those three possible strategies because column player wants to minimize the reward that is received by the row player. On the other hand, the row player wants to maximize the reward. So we see that the objective function here says maximize V. Okay, and then as before, we kind of simplified the model by substituting x2 to become 1 minus x1. So here's the linear programming model for row player. Now for the column player, we start with the same thing, which is thinking that as the column player cannot control whatever strategy is played by the row player. So we have two constraints here. The first constraint is that if the row player plays the strategy 1, and then the second constraint is if the row player plays strategy 2. And then this is the expected reward for the row player with respect to the strategies that is played by the column player. So y1 is the probability of the column playing strategy 1, y2 probability of column playing strategy 2, and y3 the probability of column player playing strategy 3. And then because these constraints are talking about with respect to each of the strategy of the row player wants to maximize his or her reward. So that's why the sign is W greater than or equal to the expected reward. However, because we are talking about the column player wants to minimize the reward that is received by the row player. Again, if you're thinking we're talking about column player, but then here why the reward is for the row player? Well, remember this reward matrix shows the reward for row player. That's why when we calculated the expected reward, it is the expected reward for the row player. So now we have the linear programming model for the row player, and this is the linear programming model for the column player. We start to solve these two linear programming models by choosing the model that has the smaller number of variables. In this case, it is the linear programming model for the row player. So this is the linear programming model for the row player. And then just like before, we start by doing some guesses, like we assume that the constraints A and B are binding. It means that we assume at the optimal solution, these constraints, they have the sign of equality. So now if these signs are equality, we may solve these two constraints because we only have two variables, v and x1, and we have two equations. By solving that, we obtain v equals 35, x1 equals 5 over 6, and x2 equals 1 over 6. Now let's solve the linear programming model for the column player using the dual theorem and complementary slackness. The dual theorem says that if we assume that this solution is an optimal solution, then the objective function value for the primal will be exactly the same for the dual. So using that result, we assume that W equals 35 as well. Now here comes the part where we are going to use complementary slackness. Complementary slackness says that the multiplication of x in primal and the variable e accessed in the dual, they must be 0. So in this case, because x1 is non-zero and x2 is also non-zero, we may confidently say that e1 and e2, they are 0 in the dual problem. Okay, so that's the first thing that we know based on complementary slackness. And then the other thing is that because v equals 35 in the primal problem, this constraint is non-binding. In other words, we have slack for this constraint. S3 equals 1, right? Because v equals 35, the right-hand side says 36. So we have the value for slack 3 equals 1. Again, based on complementary slackness, it says that the multiplication between slack variable in the primal and the y variable in the dual equals 0. So if S3 is non-zero, S3 equals 1 in the primal problem, it means that Y3 equals 0. Now let's use all this information that we've known so far. E1, E2 in the dual equals 0, Y3 equals 0. Okay, because Y3 equals 0, it means that the remaining decision variables that we have is Y1 and Y2. And originally, the sum of these three probabilities, y1, y2, y3, they must be 0. Sorry, they must be 1. Okay, y1 plus y2 plus y3 must equal 1, the sum of all possible strategies for the column player. Now, because we know y3 equals 0, we only have this equation left, y1 plus y2 equals 1. Which means that we can say y2 equals 1 minus y1. And then we replace this y2 by 1 minus y1 into these two equations. And then based on this fact that e1 and e2 equals 0, we may say that these two signs become equality because we do not have access for these two constraints, so the sign become equality. Okay, so we know W equals 35, and then we have replaced y2 to become 1 minus y1, and then the sign becomes equality. Now we may solve this and obtain that the solution is y1 equals half, y2 equals a half. So here we have obtained the optimal solution. In other words, our assumption at the beginning was correct. And then we can say this is optimal solution for both row and column player because the objective function is the same and this x is a feasible solution for this linear programming and this y1, y2 also feasible for this linear programming model. That's how we know that we have obtained the optimal solution for the game. Now let's take a look at another example. In this game, two players simultaneously put out either one or two fingers. At the same time, they must also announce the number of fingers that he believes his opponent has put out. So the player himself puts out either one or two fingers, and then at the same time, he must also announce or guess the number of fingers that he believes his opponent has put out. And this is the reward matrix for this game. So let's say if neither or both players correctly guess the number of fingers, then the game is a draw. So here 1-1 means the role player puts out one finger and say that his opponent will put out one finger. At the same time, column player actually puts out one finger, and he also guesses that the role player will put out one finger. In this case, both players are correct, so the reward is 0. Another possibility is as both of them are wrong. So for example, here 1-2-1-2 means that the role player puts out one finger, but guesses that his opponent will put out two fingers, while in reality the column player only puts out one finger. But the column player is also wrong because he guesses that the role player will put out two fingers, while in reality the role player puts out one finger. So both of them are wrong, so the reward is 0 for the role player and also for the column player. But then if somebody is correct, then that person win will win from the other player the sum of the fingers they put out by the two players. Okay, so let's say here the role player puts out two fingers and then guesses the column player will put out one finger. And then in this case, indeed, the column player puts out one finger. But then the column player is wrong because he guesses the role player will put out two fingers. So in this case, the role player wins, and he wins $3 because the sum of the fingers is 3, 2 from the role player, 1 from the column player. Okay, so this is the reward matrix, and you see that in this game there is no saddle point. And then before we proceed, to make sure that we do not have a URS reward for either row or column player, we add the constant C, which is the absolute value of the most negative amount. I believe the most negative amount is -4 here. So we add all these elements by +4 such that we get the new constraint, the new reward matrix where we do not have any negative reward, such that later in our formulation all variables will be greater than or equal to 0. Okay, I will give you a pause on this video to give you the time to read this question carefully, and I will continue after the pause. This example shows that sometimes we are not able to use the concept of complementary slackness, because in this example, the solution in the optimal solution has the problem of degeneracy. I will talk a little bit about the issue of degeneracy after this slide. Okay, so let's take a look at the optimal solution. So not only the optimal solution has the problem of degeneracy, but we also have here alternative or multiple optimal solution. So we have two extreme points. This is the first extreme point, and this is the second extreme point. Both of them have exactly the same objective function value. Okay, because these are the 2 points, if you recall the concept of alternative or multiple optimal solution, it means that any point along the line between these 2 extreme points, all those points are also optimal. How we may find those O points or find the line among those 2 points. So what we can do is we perform a linear combination using the constant C between 0 and 1, including 0, including 1. Here we multiply C times the first point, extreme point, plus 1 minus C times the second extreme point, okay? So x1 and x4, they're always 0 because in both extreme point, x1 equals 0, x1 equals 0, so they are always 0. But then x2 equals 3 over 5 times c plus 4 over 7 times 1 minus c. And then x3 equals 2 over 5 times c plus 3 over 7 times 1 minus c. It means that if you plug in any c values between these two, you will get a point, and that point is an optimal solution for the row player. Similarly, for the column player, we also have multiple optimal solution. And then to obtain the line between these two extreme points, again, you're using this concept of linear combination. Okay, just a quick review of what degeneracy means. So degeneracy happens when a linear programming has at least one basic feasible solution in which a basic variable is equal to 0. So in this example, we have a BFS, basic feasible solution, and then we notice that one of the basic variable equals 0. So this is kind of unusual because usually the variable that equals 0 are non-basic variables. Okay, so here the problem is that we have a basic variable, but the value is 0, such that when we want to apply the complementary slackness, we cannot be sure when we say that, for example, as the slack variable from the primal times the variable, the dual variable must be equal 0. If this value equals 0, then we are not sure whether y is also 0 or maybe it is non-zero, right? If we know if there is no degeneracy, then we can see for sure, for example, this s equals 6, then we can say for sure that y equals 0. However, if there is a degeneracy in our basic feasible solution, then just like this example, s2 equals 0, then we cannot really say whether y2 can be 0, y2 can also be not 0, right? That's why complementary slackness cannot be used in the previous example. So let's go back to the optimal solution of that example. For both row player and column player, we see that x1, x4 equals 0, y1, y4 equals 0. It means that when we play this game, the optimal solution means that we should never put out one finger, let's say, and also guesses one finger. Never do that. Also never do when we put two fingers and we guess two fingers. Whether you are the row player or you are the column player, you just never guess the same amount of finger with the amount that you actually put out. To show this, let's create a table which show that the column plays either 1, 1 or 2, 2. So here the column plays the wrong strategy. And the row player plays the optimal strategy. So this row 0, 3 over 5, 2 over 5, 0 means that the column player never plays the first strategy, plays the second strategy 1, 2 with a probability 3 over 5, and then place the third strategy 2, 1 with a probability 2 over 5, and then never place the fourth strategy. Remember, we have multiple optimal solutions, so this solution is also optimal. 0, 4 over 7, 3 over 7, and 0. So let's see what happens if the row plays this strategy, which is optimal, against the column who plays the non-optimal strategy. Okay, so the column plays the second strategy with the probability 3 over 5, and then place the third strategy with a probability 2 over 5. If the column player plays the second strategy, plays this strategy, but the column plays 1, 1, it means that the reward for the row player is minus 2. But if the row player plays the third strategy against 1, 1 from column player, the row player will win $3. So the expected reward for row player against column strategy 1, 1 equals $0. Not too bad. Nobody wins, nobody loses. Okay, but then against the strategy of 2, 2, first let's break down that 3 over 5 with the probability 3 over 5, the row player will play the second strategy. With the probability 2 over 5, the row player will play the third strategy. If the row player plays the second strategy, and then the column player plays 2, 2, then the row player will win $3. However, if the row player plays the third strategy and the column plays 2, 2, it means the row player will lose $4. So that's why here it is minus. And then when we calculate this expected reward for row, we get 1 over 5. Okay, we do the similar computation and then we get that for another optimal solution, the same thing happened. The row player at least reach break even. Nobody wins, nobody loses, or $0. But on the other strategy, the row player will win a little bit. But this is enough to see that the column player can never win against the row player's optimal strategy because the column player plays non-optimal strategies. So in the previous slide, we have seen that if column player plays 1, 1 or 2, 2, it is not an optimal strategy because row player can always reach break even, $0, or even win something a little bit. Okay, now here we are going to show, for example, column player again. Column player plays 1/4, 1/4, 1/4, and 1/4, and we're going to show that this is also not an optimal strategy. Okay, so suppose the column player plays this kind of strategy and the row player plays the optimal strategy, which looks like this. So x2 equals 3 over 5, x3 equals 2 over 5. Second strategy, 3 over 5. Third strategy, 2 over 5. Okay, we are going to show that the row expected reward is 1 over 20. Again, it means that the row player will win just a little bit compared to the column player if the column plays this strategy. How can we compute this expected reward for row player? Well, we just list out all the possibilities. So the row may choose either the second strategy or the third strategy. And then the probability of row chooses the first strategy is 3 over 5. So we write down 3 over 5. And then the probability of row choosing the third strategy is 2 over 5. So we write down 2 over 5 here. Okay, now because the column player plays 1/4 for each of the possible strategy, so we have 1, 1, 1, 2, 2, 1, and 2, 2, and pair it with the strategy of the row player. Okay, 1, 1, 1, 2, 2, 1, and 2, 2, and then put the reward here. For example, the row chooses 1, 2, column chooses 1, 1, the reward is minus 2. So write down the reward here. And then this probability 1/4 for all this, because again, remember, we are supposing that the column player plays this strategy, 1/4, 1/4, 1/4, and 1/4. So now we have the probability of occurrence of each pair of strategies. Now what you need to do is just multiply the probability with the reward and then take the sum. such that you will get that the sum of all this multiplication and probability times reward equals positive 1 over 20. In other words, the row will be expected to win 1 over $20 against non-optimal strategies from the column player. Okay, so we have seen two examples in which sometimes we may use the concept from duality and complementary slackness to solve the problem. Sometimes we can't. And then here's an exercise for you to try. So try to formulate this game. And then in the next video, I'm going to talk about another type of game, which is called two-person non-constant sum game. So see you on the next one, and thank you. In the previous videos, we've seen that we may use the graphical approach to solve the games in which each player has two strategies. Now here we are going to talk about how we may use linear programming to solve the games in which each player has more than two strategies. So let's start.